So, we continue with our discussion on some emerging technologies for implementing logic gates. So, we talked about all optical implementations in the last lecture. In this lecture, which is the second part of emerging technology, we shall be talking about a very interesting technology called Memristors. Memristor is actually a combination of the two terms memory and register. Let us try to understand what memristor is. Well, the presence of memristor was first predicted in 1971 by a professor Leon Chua, who considered this device as the fourth fundamental circuit element, passive circuit element. Now, you know that we have some fundamental circuit element that we know about: resistor, capacitor and inductor. And also, if you look at the relationship, voltage and current are related by V equal to R I, voltage and charge are related by Q equal to C V. These are well known equations we have studied in schools, right. Current and flux are related by phi equal to L I, and also cross relationship is also there. D phi dt is nothing but the voltage, and dq dt, rate of change of charge, is the current. Now, you see, we live in a world where symmetry is seen everywhere. So, Chua's first argument was that something is missing, there is a missing link. Then he theoretically postulated that there should be another such fundamental circuit element which should connect flux and charge. So, this phi equal to mq, this was the relationship that this new device should exhibit, and this new device he gave the name memristor. But forgetting this theory behind it, essentially speaking, a memristor is a device whose resistance changes in response to an applied voltage. Not only that, it can memorize the last resistance value even when we switch off the power, we withdraw the voltage. This is a very interesting property. Let us see. Very briefly speaking, you see, Leon Chua predicted the presence of memristor in 1971, but it was much later in 2008. So, it is about 37 years later. Means a team from the HP Labs USA, they fabricated a device. They did not knew what the device was, but they saw that it is exhibiting some very peculiar properties. Later on, they looked at the paper by Chua and they saw that, well, the properties are very closely matching with what Chua had predicted. So, they accidentally fabricated a memristor. So, how did they fabricate the device? They use a material like here is shown in the figure. They created a device where on one side there was a region of pure titanium dioxide, and there was a other side, this was also an oxide of titanium, but with some oxygen vacancy. This is called oxygen vacancy, because in TiO2 the number of oxygen atoms is double that of titanium, but you see it is TiO2 minus X some. So, one such oxide is Ti4O7, something like this was put here, and on the both sides for connection they used platinum. So, in this device what they found, okay, the size of the device was very small, cross section area was as small as 9 nanometers square and the length was 10 to 12 nanometers. Now, they observed, okay, symbolically they represented this device like this. This was actually proposed by Chua. The side where there is this oxygen vacancy, this part is solidified, and this symbol is like this. This is the symbol of a memristor. So, the idea was that if I apply a positive voltage on this side and a negative voltage on this side, then what will happen? This boundary will be moving to the right, because oxygen vacancies are positively charged. They will be repelled by this positive, they will be moving right, and this is a region of low resistance and this is a region of high resistance. So, the low resistance region will be expanding, the overall resistance will decrease. But if I apply a reverse voltage, then the boundary will be moving towards this direction. So, this oxide region will be shrinking and the titanium dioxide region will be expanding. So, the overall resistance will be increasing. So, just by applying a voltage of a suitable polarity, I can either reduce the voltage or increase the voltage. Now, another interesting property was that this oxygen vacancies has a very unique property, that if you withdraw the voltage, they will remain in the position they were the last point in time. So, they will not change, which means the change in resistance that has taken place is non-volatile in nature. What is meant by non-volatile? Some change is said to be non-volatile if it remains even when I have withdrawn the voltage or the power supply. Here it is something like that. I can change the resistance by applying a suitable voltage. Then if I withdraw the voltage, the old resistance value will remain. The device will be remembering the resistance. So, you can understand that I can implement a very simple memory device using this. It can memorize the resistance, right. So, very briefly let us talk about the characteristics of such a device. These have been quite widely studied by many researchers. Voltage and current characteristic exhibits this kind of a behavior. It is called a pinched hysteresis loop. There are two regions, you can see one here and one here. So, this can be approximated by a curve like this, one with a low resistance. See, this is voltage and current. So, higher slope means low resistance for the this is current here, voltage, the reverse, and this will be R of is high resistance, because this current voltage, slope means current is smaller, resistance is higher. So, there are two distinct resistive regions, low resistance and high resistance, and I can switch from one resistance to the other by applying a suitable voltage. If I apply a voltage V open or any voltage beyond that, let us say V clear, then it will switch from R on to R off, R on to R off. But if I apply a voltage, negative voltage beyond V close, then it will switch from R off to R on. So, I can switch from low resistance to high resistance or high resistance to low resistance by applying a voltage of suitable polarity. Now, this property that a memristor can remember the last resistance value, it makes it very useful for implementing memory devices, storage, and we shall see it can be also be used for implementing some gates, logic design. So, we shall very briefly look at this technology. So, we have already said memristor is something which is very small in size, much smaller than the current CMOS transistors. Well, it consumes a little power only during operation, but when you are not operating, you can withdraw the power. So, there is very low power consumption, it can remember the last resistance, non-volatile. Crossbar structure means you can have a very compact implementation, some rows and columns. These are two different rows, and you can connect the memristor between rows and columns like this very conveniently. etc. This is called a crossbar structure. Some of the applications just to name, one is we can use this to implement memory systems, non-volatile memory systems. This is called resistive random access memory, resistive random access memory, resistive RAM. We can model brains. There is also some work where some neural networks or some neurons were implemented using memristors, and of course, we can implement gates, some digital circuits. Okay, so we are not going into the detail of this because this is slightly beyond the scope of discussion here. I just wanted to name a few applications. Now, let us briefly look at how we can implement logic gates using memristor without going into much detail. We shall be talking about two broad techniques. One is called memristor aided logic, in short magic. Now, using magic you can implement any of the gates, AND, OR, NOT, NAND, NOR. And in this method, you see, for a conventional gate, when you are implemented using TTL or CMOS, these inputs we were applying as voltages and the output we are getting as voltage. But for a circuit using memristor, it is different. We call it stateful design style, where we apply the inputs not as voltages, but as resistive states of the memristors. The meaning is something like this. Suppose I am implementing a gate with two inputs. There will be two input memristors. By applying a suitable voltage, I shall be initializing those memristors to either the high resistance or the low resistance states, right. If it is high resistance, I call it logic 0. If it is low resistance, I call it logic 1. So, the inputs I am not applying as voltages, but I am applying as resistance values in the memristors. This is called stateful logic. Okay. So, this is the convention, and in memristor aided logic, when you carry out a gate operation, you have to initialize another memristor where the output will be stored. So, we initialize it to either 0 or 1 depending on the type of the gate, and some voltage has to be applied on the input side to evaluate the gate. I will just show you how this circuit looks like. Here I have just taken an example of a NOR gate. This is an n input NOR gate. There are n number of inputs and one output. Now, you can very easily implement it using memristor like this. There are n number of memristors x1, x2 to xn, which represent the inputs, and one memristor representing the output. In the previous slide I mentioned, for NOR gate, this output memristor must be initialized to the 1 state, which means on, and depending on the inputs, you will have to initialize these input memristor. Suppose the inputs are all zeros. Because it is a NOR gate, when the inputs are all zeros, the output has to be 1. If the inputs are all zeros, means what? These are all high resistances. So, this V 0 is connected to this point, V 0 is connected here. Because this is a high resistance, very little current will be flowing, and these are all connected on this side. And because this is high resistance, no current will be flowing, and this point is grounded, and this point will be approximately at the ground potential, ground. So, on the output memristor there will be no current flowing, and it was 1, it will remain as 1. So, it remains as 1. But let us say at least one of the input is at 1, let us say the last input is 1. So, for a NOR gate the output should be 0. Let us see how it happens. Let us say one of them is 1, means this xn, let us say this is on, this is 1. this is the on means V0 will be connected through this is a low resistance, and this will not be ground, this will now be V0, and this V0 will be applied across this memristor. See, this spot is ground, this point is V0. So, you are applying a higher voltage on the other side and a lower voltage on the that TI 407 side. So, this will be reverse biased and the output will be changing to 0 to off. So, this is how it works. Now, not only like this, you can also connect it like this in a different way, where of course, the connections will be different, but I have just shown this to you just for your convenience. Okay. This is one way you can implement some gates using memristors, just to give you an idea. And there is another kind of a logic design style which is also quite widely explored. This is called imply function, and imply function is defined like this. You take the not of a variable a and then do a OR. This is defined as imply function. Now, using memristor you can very easily implement imply function also. Now, it can be shown that imply function along with constant 0 is again functionally complete. Like for example, if b equal to 0, if b equal to 0, then you can implement what? A bar or 0 means it will be a bar. That means you can implement not operation. So, since you can implement not operation, then you can just apply the input a was there, you apply a bar and then imply b. This will become a or b, which is OR operation. So, you can implement a not, you can implement an OR. This again is a functionally complete set, as we shall see later. So, you can realize any arbitrary function also using imply. So, here I am not going into the detail, just to give you a basic idea that this memristor is a very promising technology and you can use it for designing logic also. An imply gate can be realized like this: 2 memristors and 1 register. The convention is that the inputs will be stored in A and B, and after operation the output, that means this A implies B, this will be the output, this value will get stored in B. So, the value in B will be overwritten. So, again the voltage you are applying here is V cont and V set. I am not going into detail here. So, the basic concept is like this, that you have a circuit comprising of 2 memristors and 1 register. So, whenever you want to carry out some logic operation for some given value of A and B, let us say A equal to 1 and B equal to 0, then you will have to initialize the values of A and B appropriately. Let us say I initialize A to on, I initialize B to off, then I apply V cont and V set, then this A bar or B will be 1. So, what will happen is that after computation B will become 1, this will be the output, because output will also be stored in memristor B, right. So, actually this is how the imply gate works. So, here in this lecture we have given a very brief idea without going into the detail regarding how this emerging technology memristor works. So, if some of you are interested to know more about memristors, you can read the literature. If you do a Google search, you will get a lot of material about memristors and lot of interesting applications that people are talking about. So, a few things people are predicting, that the first kind of application of memristor that you will see in the market will be some non-volatile memory devices like the pen drives, USB drives that we use today. They will be of much higher capacity, much faster as compared to the present day USB drives. So, let us hope that we get to see such devices in the market very soon in the near future. Okay. So, with this we come to the end of this lecture. Now, from the next lecture onwards, we shall be starting our discussion on so called switching functions and switching expressions. How do we represent such functions? How do we manipulate? How do we minimize? And later on we shall see how do we implement them using gates and various other circuit modules, digital circuit modules to implement the desired functionality. So, we shall be starting this discussion from the next lecture. Thank you.